Hello, everyone. Hope you're all doing well. Sorry, I tried to squeeze in a run right before lecture. Do you ever get like really motivated and then sign yourself up for something totally stupid that you don't want to commit to? Because that's what I did. My friend and I are now running every day, a 5K every day for 30 days. And I'm on day 6 and I'm dying. So that was the only time I was going to be able to get it in. So sorry. But we'll see how it goes. Day 6, I'm pretty sore. I was calculating, running sucks. Yeah, running does kind of suck. And I have 24 more days. I think I'll be doing my last day when you guys are doing your final. I'm not that far away. All right, let's do another example, or I want you to work through an example. Share my screen of those heating curve problems. So I've got one for you here. And this says, how much energy is required to convert 105 grams of liquid ethanol at 25 degrees Celsius to gas at 200 degrees Celsius? The specific heat of the gas is 4.67 joules per gram degree Celsius. The specific heat of the liquid ethanol is 2.57 joules per gram degree C, and the specific heat of gaseous ethanol is 4.67 joules per gram degree C. Ethanol boils at 171 degrees C. There's one more piece of information. I need to give you the fusion. So heat of, no, just the heat of vaporization. Vaporization is 38.56 kilojoules per mole. And if you're wondering what ethanol is, it's C2H5OH. Okay. So you do kind of need that to work the problem. So I'd recommend first start by drawing a heating curve. It's different than the one we worked on before where we had water parameters. And I'm going to let you all keep working on the problem, but I'm going to draw my heating curve so that you can kind of get an idea if you're head in the right direction. So just make sure your Hayden curve looks something similar to this, at least numbers in the right spots. Give you another 2 minutes. All right, so with this problem, I would recommend drawing a heating curve just to kind of organize the information. So what we have is we have liquid ethanol and it's at 25 degrees Celsius. And we want to raise it to a gaseous 200 degrees Celsius. So what I have to do is start in my liquid phase at 25 degrees Celsius. Now, before I can convert into a gas, I have to bring it up to whatever the boiling temperature is for this substance. So for this substance, it says it's 171 degrees Celsius. If this problem was talking about water, that would be 100 degrees Celsius. All right, so the first step or the first limb of this is going from liquid at 25 to liquid at 171. So let's just do that now. Anytime we have this temperature change, which are the slopes, that's where you use Q equals MCAT. Q equals MC delta T. So for this one, we have our mass, which is 105 grams. We need to use the specific heat for the liquid because we're in the liquid range. So 2.57 joules per gram degree C. And then my change in temperature, 171 minus the 25, 146 Celsius. Remember, it's always final temperature minus initial. So we'll cross out our Celsius and our grams, multiply it by 2.57. And I get 39,000. I'm going to keep all those numbers and just round at the end, 39,398. And this is going to give it to me in joules. All right. 2 is the flat area here. This is a phase change. So we need to determine what phase change we're doing. And in this, we're doing vaporization. So this is the number we would use. Oops, sorry about that. If it gave us heat of fusion as well, we just wouldn't use it in this problem. So I know how much I have. I have 105 grams of this ethanol, C2H5OH. But if you notice, my energy is related to moles in this. So I need to get out of grams and get this into moles. 1 mole of this is 46 grams, the C2H5OH. So then I'm going to take that number and I'm going to multiply it by my heat of vaporization, which tells me that I get 38.56 kilojoules for every 1 mole. My moles will cancel. And in this one, 105 times the 38.56 divided by 46. I get 88.02 kilojoules. Now the problem said, it just says how much energy. So this is in joules. I know this other thing's going to pop it out in joules. So I'm just going to convert this to joules while we're here. So 1, 2, 3, 8. Actually, no, I'm going to convert this to kilojoules because the numbers get kind of big. So 1, 2, 3 kilojoules. So this is 39.39 kilojoules, 88 kilojoules. And then we've got one more leg. This step raised the liquid up to the vaporization temperature. This step phase changed it. Now we need to take, once we get to the end of this, we assume that we're all gas. Now we need to take our gas up to a temperature of 200 degrees Celsius. So the third step here is similar to the first step in that we use Q equals MCAT, but we need to change our specific heat. So our mass is still 105 degrees Celsius, 105 grams. Our specific heat changes to the gaseous specific heat, which is 4.67 joules per gram degree C. Those numbers would have to be given to you, okay? So you don't have to pull those out of thin air. And then our change in temperature will be 200 minus the 171, or a change of 29 degrees Celsius in gaseous form. So for this last guy, I think I put the wrong number in there. I get 14,000. 14,220 joules. Again, let's convert it to kilojoules. 1, 2, 3, so 14.220. Then I'm gonna, the final step here is that I have to add all of them together. So I need to take 1 plus 2 plus 3, or 39.398 kilojoules plus 88.02 kilojoules plus 14.22 kilojoules. Right, and we end up with 140, I'm gonna go with 142 kilojoules. So to move through this entire process would take 142 kilojoules. Any questions on that? You'll be given a lot of information in those problems. You just kind of have to file it into this heating curve. All right, so let's move into the next section here. So whereas a heating curve was just showing us the temperature, and then this is just sort of arbitrarily adding heat, right? We are increasing the amount of heat, we increase the temperature, and we go through our phase change. A phase diagram is going to plot pressure versus, this is not pressure versus time, it's pressure versus temperature, okay? So we're looking at a relationship between pressure and temperature, whereas in a heating curve, your possibility for numbers is just on this line here, right? We don't have values over here, values over here. We trace this linear equation here when we're looking at pressure and temperature, because we have two variables. Everything on this chart is an area that comes into play, all right? So we're not just tracing a line, we actually can exist in any spot on this diagram. So depending on what temperature and what pressure we're at, we can use one of these to figure out what phase we're going to be in. Because temperature isn't the only thing that dictates phase. Pressure also dictates what phase we're in. If we're under a very high pressure system, it will force your molecules together. So it can actually force a liquid to become a solid or a gas to become a liquid if we have a high enough pressure. Vice versa, if we have a really low pressure environment, like down here somewhere, okay, we can actually have what would be normally a solid. Ooh, we drop that pressure just slightly and it can become a gas. So these lines are representing separation points between our phases. Green is solid, blue is liquid, yellow is gas. And so hopefully that makes sense. You know, if you're at a high temperature, you would expect to be in a gas. As you lower your temperature, you would expect to move into liquid and solid. Pressure has a secondary effect, right? So as I increase pressure, it sort of shifts my ability to be a solid into the higher temperature range, right? Down here, I'm a solid when I'm at this temperature, but if I increase my pressure, I can actually extend my solids to a higher temperature because it's holding it together. So there are, we've got a point here. This is where our three phases combine. This is known as a triple point at this specific pressure and temperature. And you can see that there's not any numbers on here. So this is just a generic phase diagram. They do have ones where they're for specifically for water or CO2, but this one's just generic. At that triple point though, we actually get an equilibrium where all the phases exist simultaneously. So we would see solid, liquid, and gaseous. We have our vapor pressure curve. And this generally, as pressure increases, temperature will increase. So here's our vapor pressure curve. Here's our fusion curve. This is the switch between solid and liquid. This is the switch between liquid and gas, vice versa. Over here, this is sublimation and deposition. This is going straight from solid to gas or straight from gas to solid. Those things tend to happen at very low pressure situations. We have a critical point that you can find up here at B. This is a specific temperature and pressure where the material doesn't really like to exist. It kind of starts to fall apart. Think about what's happening at this area of the diagram. We have a really high pressure. So the pressure is pushing the material together. But then we also have a really high temperature that's pumping all this kinetic energy into it. So the molecules or atoms want to get really far away from each other because of that temperature, but they can't because of the pressure. So it becomes kind of a tricky situation. We've got our melting curve, okay? Melting curve. As pressure increases, the solid gas is favored if the solid is more dense than the liquid. Excuse me. And then we have our normal, when they say normal melting point, that's referring to the melting point or the melting temperature at 1 atm. So normal meaning 1 atmospheric pressure. So looking at some of these points, we can decide what we would expect to see as far as our phases. So at point A here, our triple point, we would expect to see solid, liquid, and gas of whatever this material is. Point B, okay, point B is that critical point. We would see liquid and gas here, but they'd sort of be indistinguishable from each other. So it would sort of be like almost a slosh of liquid gas. They're sort of sitting in between those two. Can't really make up its mind. If we're on line A to B, so this right here, or our vapor curve, this is where we would expect to find both liquid and gas, right? Because right along this line, we're phase changing. And those two would be in equilibrium. Along A and D here, we would expect to find solid and liquid. We wouldn't expect to find any gas over here. And again, this is while the phase change is happening, both of them are existing. And also note when we're phase changing, we don't see a temperature change. And then A and C here, this is where we would have solid and gas. So direct sublimation or deposition happening. We wouldn't see any liquid along this line. So let's look at a couple phase diagrams for actual materials. I've got water on the left here and CO2 on the right. So you can see that they have slightly different regions, right? The this line here, where we go from ice to water vapor, is a lot shorter than the line for solid CO2 to gaseous CO2. And so a lot more opportunity, a lot more pressures and temperatures where we can have sublimation happening or deposition. Remember normal, if we're talking about normal conditions, we would say it's 1 atm. So on these diagrams, I would say that this here and this here would be considered our normal conditions. Um, 1 ATM. So under normal conditions, if I wanted to know what the melting point of water is, I would go over to the line where I'm changing from solid to liquid, which would be this point right here at B. And then I drop down and I could see what the temperature is. And what we find is that the temperature is 0 degrees, which is pretty consistent with what we know about water, right? At 1 ATM, let's say I want to know what my boiling temperature is for water. I go over to that place where the phase change is happening. In this case, it would be C, and we drop down and we get our 100 degrees. So those are consistent. So looking over here, at 1 ATM, we actually don't have any situation where we have liquid. So we don't have a melting point under normal conditions for CO2. What we have is a sublimation point. So at 1 ATM, if I move over to Y and then drop down, what I'll find is that at negative 78.5 degrees Celsius, I will go directly from a solid into a gas. So if you've ever had dry ice, right, and you use it at Halloween and you get all that like sort of fog effect, that's just CO2. It's just gaseous CO2. So take a look at this diagram here and tell me for CO2, what phase is CO2 at 0.05 ATM. Oops. And and 0 degrees Celsius. Okay, I'll give you an X and a Y. So go ahead and look at your diagram here. Figure out in what region do we see CO2 at half an ATM and 0 degrees C. Okay, so you just think of this like you would in one of your basic graphing math classes. Look at your ATMs, that's on your y-axis. 0.5 is somewhere right along here. 0 degrees Celsius is somewhere over here. Okay, so I'm going to bring this over to somewhere in this vicinity. It doesn't even matter exactly where it is. There's no other possible way that this could be anything but a gas. Ask yourself, what is the boiling point of CO2 at 73 ATM? Okay, so 73 ATM is actually already marked for us here, and we've got our dot, 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 dot. So we just have to find the line that signifies boiling. This one is not it. This is going from solid to liquid. That would be melting. So we want to go all the way over to point Z here and drop it down, and it tells us, hey, we'll boil at 31.1 degrees Celsius. But 73 ATM is a very high pressure system. That's 73 times more pressurous than us at sea level. Okay, so the last thing that we've got on here is just sort of a review of all the different types of bonds and forces. So our weakest are going to be these London dispersion, dipole, and hydrogen bonds. So say weak. And these are all strong. Sometimes we like to call these three as well primary. forces, because these are like the main things that are holding it together. These are sort of secondary forces. These tend to do more subtle things. This is what sticks X and Y together. These start to allow X and Y to create a molecule that curves or bends or does things like double helixes in DNA. So that really need to go over that. It's kind of already what we've talked about. But yeah, that's actually it for this chapter. I think it's like one of the first times we were able to finish early. If you guys want to do another problem, if anyone wants to stay around and work on something from this chapter, let me know. We are meeting on Tuesday of next week, so please be around, but then obviously Wednesday, Thursday, school's closed. So have a really good weekend, and I'll see you on Tuesday. Unless you want to hang out. If you want to hang out and work on something, let me know. All right. Enjoy. Bye, everyone, or most of you.
Thank you.
Bye. David, you have a question? Yeah, give me a second, okay?